All right, so now I'll talk about the Magnus expansion. Okay, and so I'm going to consider solutions of the differential equation y prime is equal to a of t y of the form y of t is equal to the matrix exponential of theta of t y0, right? And then you know it's like from previous discussions that this theta of t satisfies the following equation. Okay, so theta prime is equal to dx theta inverse applied to A, right? So this sort of dx inverse map is what pulls back the vector field from the group. It's like back to the algebra, if you will. Okay, and then there is an explicit expression for this. So this is, well, I mean, it's an expansion. I would say k equals to 0 to infinity, bk over k factorial, the little add operation, which is just a commutator, if you recall. All right, so the bk's are the Belloni numbers, okay, and then the initial condition is that theta at 0 is just 0. Okay, so what we're going to try to do is we're going to try to solve this differential equation. It's like for theta, and one possible way to do this is through what is called Picard iteration. Okay, so we can solve this by Picard iteration. And if you haven't seen Picard iteration before, it's basically a fixed point iteration which comes from considering the fundamental theorem of calculus, right? So you know by the fundamental theorem of calculus that y of t is equal to y of 0 plus the integral from 0 to t of f at y tau d tau. And the basic idea then is that you start the iteration by letting the initial guess, it's like be just y at times 0, it's like just a constant solution. And then what you do is you take that initial thing, you substitute it to the right hand side, and you evaluate that. You evaluate this integral plus the initial data. That gives you a new value for y, right, a new iteration for y, and then you're looking for the fixed point of that map, basically, right? So, all right, so when you apply this, it's like to this setting, what you have is that you start with theta 0, if you will. Let's call that theta square bracket 0 of t is just identically 0 because the initial data is 0, right? Then the next thing you do is you apply, it's like this equation. All right, well, so let's just write this more generally. So let's see, the mth plus first iterate, it's like theta, right, at time t is just, well, the initial data, which is 0, okay, so plus just the integral from 0 to t of this, derivative term, which is the exponential of, and then theta shows up here, so we just put theta, but from the previous iterate, okay? And then inverse applied to A, okay, and then cos C, D cos C. All right, so that's basically what that Picard iteration does. It's again an example of a fixed point iteration, okay, where the fixed point equation is coming from the fundamental theorem of calculus. Okay, so since we know that this dx inverse has this series expansion, we can write it in terms of the series. So this is the sum from k equals to 0 to infinity of bk over k factorial, right? The integral from 0 to t of add to the kth power of theta, the mth iterate of theta, okay, depends on c. Okay, and then a cos c, I should write this, cos c, d cos c. Okay, all right, and then this is true from m equals to 1, 0, 1, and so on. Okay, so then the Picard theorem, which is of course some sort of fixed point type convergence of a fixed point theorem iteration type argument, right, using some sort of contraction mapping kind of result, right? So Picard theorem basically implies that this sort of iteration has a limit, right? So it converges, right? So then sort of the Picard theorem sort of implies that theta of t, which is the limit as m goes to infinity of theta mt, right, exists for sort of sufficiently small things, right? Then the claim is that this leads to the Magnus expansion. So maybe let me write it up there. Okay, so this yields the Magnus expansion. Okay, which is that theta of t is going to be some linear combination. So k equals to 0 to infinity of these hk terms, right, where hk is a linear combination of k plus 1 integrals of k commutators, basically. And I'll show you what I mean by that. Okay. All right. So I should say that it's not so surprising because again, it's like if you think about what's happening in the Picard iteration, right? Every time you apply one more step of the Picard iteration, you are applying the fundamental theorem of calculus to a function which is defined in terms of an integral, right? So every time you add one, there's an additional iterated integral you have to have. And the add operation, right, the little add operation involves commutators. So it's not so surprising that when you keep applying this correction coming from the Picard iteration, you get a combination of terms which involve iterated integrals of iterated commutators. Okay, so that's basically what's going to happen. So, so h0 of t is going to be the integral from 0 to t of a cos c1 d cos c1. So this is of course just the sort of the simplest case. That's like which we have from before, right? Which which you always have even in the scalar sort of linear equation case. And then h1 of t is minus 1/2 the integral from 0 to t of the integral from 0 to cos c1 of a cos c2 d cos c2 paired with a cos c1 d cos c1. Okay. All right. So this h1 term has two integrals, right, and one commutator, which is sort of what I basically said. And then the h2 term, right, is going to be 12th integral from 0 to t. All right, integral from 0 to c1, a cos c2 d cos c2, comma, integral from 0 to cos c1 of a cos c2 d cos c2, a cos c1 bracket d cos c1. Okay, so this term, so there's actually another term, but let me talk about this term first. Right, this term has three integrals, right? and 2 commutators, which is again of that form which we talk about, that the hk term has a k plus 1 integrals of k commutators. Right. Okay, so the second term looks like 1/4 integral from 0 to t, integral from 0 to c1, another commutator, bracket, integral from 0 to c2 of a c3 d c3, right? D c, oh, sorry, a c3 d c3 paired with a c2, close bracket, d c2, a c1, bracket, d c1. Okay, so like the other term, it's like, so this is k equals to 2, so you expect 3 iterated integrals and 2 commutators. So you see 2 commutators, and you see 3 iterated integrals. All right, so this sort of keeps going on, but at least in principle, it's like that gives you then a way of computing higher and higher order corrections. And as you might expect, it's like the way you might actually implement this in practice is to maybe use some sort of quadrature rule to approximate the integrals here. Okay, so let me just stop here for now. Thank you.